Okay, 4.7a, intro to inclined planes, normal force, etc. And on the worksheet, you'll do number 2 and 3. Now, you can look at your note. You know what? There's not really a need to look at your notes because section 4.7, your notes is just this. It just has some problems to work, which are word problems that we'll get to next time. But what I did is this is a challenging section, okay, in this chapter, but it's kind of a fun section too. So I'm going to kind of teach you a little bit of physics art as well as the math stuff involved. So I have on a piece of paper, you got that one, you can download that one. There are 3 different inclined planes and diagrams, and I'm going to do number 1 for you. Then I'm going to have you do number 2 and number 3. Okay, so let me just write this out. I'll call it 4.7a. It's an introductory lesson, and it says, okay, number 1, the mass of the box equals 10 kilograms. I'm going to teach you some terminology also by doing this question. The angle is 20 degrees, and then it looks like this. Actually, I'm going to introduce a little something at the beginning of it before I show you how to do it. I think I'm going to tell you a little thing interesting about acceleration. So you know that if I mentioned this in the last lesson, kind of at the end of it. If I have an object like, okay, here's my little ball bearing there. If I drop this from, let's say there's a slide, like little kids go up a slide. I mean, they don't really look like that. I mean, there'll be a ladder here. We can do a ladder if we want to do a ladder. And there'll have a little slide right there. You don't really see this part. There is an angle over here of incline. That does matter. And in fact, I'll let that be 20 degrees as well. So I'm going to kind of add this in first. Here's a 20-degree angle. Now, first, when they go up the slide, you would never just go like, okay, they're going to go down, they're going to end up on the ground. And you know, they might come down here and then you kind of hit. Hopefully there's sand or something kind of soft, or now they have the padding everywhere. We never had that where I grew up in Alabama. I'd probably slide down, hit a piece of concrete and stuff. So, but anyway, I don't know if it's that bad, but anyway, it rolls down, hits. Well, what would you rather do? If we say at the top, would you rather say, okay, I'm going to push you down the slide. I'm going to push you down this way, boom, or I'm going to push you down this way? Which one would you rather have? Obviously, you'd rather go down the slide, because see, even the only thing that would slow down slow you down, I'm just thinking about that, would be like the friction against the side of the slide. Now, we're not even talking about friction yet. But if that slide were even like a water slide, like with water going down, or if it was completely wet or oiled, like oil, that would be better. If that thing were oiled and you were to slide down that thing, you'd go so fast, you know. And just say if it were oiled and you had oil on all your clothing and stuff, we just completely covered your clothing with oil and oil there. You're just going to slide down that thing quick. You can't even really, boom, you're just going to go amazingly fast, like no friction. But still, this would not be as bad, boom, as hitting as it would if you were to fall straight down. So an inclined plane does affect the way that you're accelerated by gravity. So it's going to be different down an inclined plane. Obviously, it's going to be better, going to be easier. Well, I just wanted to show you this one little thing. And then what I'm going to do is, I'll say the opposite is also true. But it's easier if I've got to get this heavy, see how a heavy box. It's easier to push the heavy box up a slide or a ramp instead of trying to lift it straight up here. Okay? It will take, in the end, you'll not have to put the same force all along the way. You'll put the force over a longer amount of distance here than you would here. Now, it kind of gets into a later chapter called work, the next chapter we would do. I'm not telling you everything here, but you know that's true. You know that it will be easier to push up, or even a very heavy person or a heavy box. It'd be easier to push them up the slide, you know, little at a time, little by time, little at a time. You can do it, all right? But if you had to lift them up, you might not even be able to do it. Like you could have, like imagine someone that's a lot larger than you, and you have like a smaller maybe not a real small child, but like a just say like maybe a middle school trying to push like a real big football player from senior varsity football player, really big guy, lineman, and somebody like a middle school student would be trying to push them up. So they could not possibly lift them up. That can't be done. But if they're on the slide, they could be able to push them. So anyway, so why is that? All right, mathematically, it has to do with a change. I'll show you this. Gravity only acts in this direction. So I could even write down, if I wanted to, this could be the acceleration of gravity. I don't know if I want to show you this all right now or not, but well, I guess I will. Okay, I'm going to draw A straight down. This is 20 degrees. I want to use another color because this is going to be a little confusing. Well, just watch what I'm going to do. In a moment, I'm going to draw another picture, but I'm just going to show you something here. We know that the acceleration of gravity is 9.81 meter per second squared. All right. Okay, that's this right here is 9.81. Now watch this. What I'm going to do is I'm going to draw a line perpendicular to the surface. So I drew one line perpendicular. Notice how I did that. I'm going to do this a couple of times for you. Perpendicular to the surface. Now I'm going to do this. I'm going to connect these two. And I'm going to make another line this way. So here's what I'm trying to do. This represents A, the acceleration of gravity, which is 9.81. I should probably have put it right there. So if you go straight down this way, off the side, as you accelerate, you're accelerating at 9.81. That's your acceleration. But now, here's what I want to show you. Watch this. I want you to notice, if you draw this diagram, that this bottom part of this triangle is parallel to the surface that you slide down. This other component, the y, we'll call that AX and AY is perpendicular to it. Now, there's another word for perpendicular. I'm going to tell you that in a minute. I don't want to confuse you on this one problem. Now, here's what I want to show you. This angle right here is equal to 20 degrees. So now we want to look at a little bit of geometry. You might have to zoom it in, or I hope you can see that. Can you see the numbers pretty good on the video? All right. So let's take away the 9.81 for a moment. If this angle is 20 degrees, okay, notice that this line comes down, the acceleration. We have two triangles. We have a triangle here, and we have a triangle there. Okay? In this triangle, we know that this is 90 degrees. Right? You know that because this is perpendicular to the ground going up. So that's 90. That's 20. That angle would have to be what then? 90 plus 20 plus the other should equal 180, right? So 90, 70. This is 70 degrees right here. Now, you're not going to really have to draw that 70 degrees very much, but I want you to see something. Okay, this is 20, 90, that is 70. Now, okay, I know you might have to pause it and go back and watch and think about this. Now, look at this angle at the top right here. If this is 70, notice that on the top surface, this next AY is perpendicular to the surface. So if AY, this white line from here, it's white and orange, but this one over here is perpendicular. If this is 70 degrees, what must this next angle be? 70 and what? Well, it must be 20. Aha! Hopefully you see that. So, what we're telling you is that this angle at the top of the triangle is equal to this angle. When you make a diagram this way, this is 20 degrees, that is also 20 degrees right there. Okay? And the reason is because that's 90 and that's 70, and 70 plus 20 should give you 90 again for that angle. Now, you're not going to have to do writing these around on a lot of them, but if you draw your picture correctly, this angle will always equal that angle, or vice versa. That angle will always equal this, and then for that matter, this would also be, that would be 20, and that would be 70 down there. And we don't really need this bottom angle here. Now, why does this matter? Okay, why does it matter? Well, I wanted to show you. If I drop this ball straight down, gravity will accelerate at 9.81. So A is equal to 9.81. But now, is AY doesn't even matter in this problem, because when you go down a slide, you're not going down this way, you're going this way. You're sliding this way. So what would be your acceleration in this direction? Sorry. You could call this one AX. You're only going to accelerate the X component of the acceleration, of gravity. You're not going to accelerate, when you go down here, you're not going to accelerate 9.81. You're only going to accelerate at AX. And how would you find AX? Well, you look, here's the angle, opposite over hypotenuse, and that would be sine. Sine of that angle would be AX over A. Okay? Now, we're saying that A is the full acceleration of gravity, 9.81, and the angle is 20. So sine of 20 degrees equals AX over 9.81 meter per second squared. So, now this is not on the worksheet, but I wanted to show you this now. It might pop up at some point. So sine of 20 is 0.342 equals AX over 9.81. And then 0.342 times 9.81 equals 3.35 equals AX, meter per second squared. So look, gravity, if you just drop straight down, gravity won't accelerate you 9.81 meter per second every second. Okay? But on this slide, as you go down, if there's no friction, if it's real slippery surface, wet or has oil or whatever, you'll slide down at 3.35, only about 1/3. You know, that actually is kind of funny, but that actually might be close to what the acceleration is on Mars. I know that Mars has a lower acceleration of gravity than the Earth does. So what that would mean is that, a little child could not jump. Well, if they jumped off this way, they might break their leg and might hurt them. But sliding down here is not a problem. But on Jupiter, they could jump off. You could jump off this side; it would be no problem at all. It wouldn't hurt your muscles or anything, because you're not accelerating that much at all. You're not as you come down. Okay, this is a kind of neat thing. I hope you thought it was cool. That's how I wanted to show you this. So there's acceleration in my drawing, A, and then there's AX and AY. Only AX is the acceleration that affects you. Okay, all right. So let me go and do the problem now. This might pop up from a problem or textbook problem, or a problem like that could arise. I could ask you to find the acceleration of gravity, the component of it, but not now, not today, not on this particular lesson. This is dealing with the normal force. So we're going back to this problem. I went backwards, and it's going to be what I showed you. I could use it for this one, but I'm just going to start over again. All right, so I'm going to draw a triangle, slide. I'm just going to make an inclined plane this time. I'm going to try to get larger, so maybe it'll be easier to see my diagramming. Okay, now it says there's a box up here, mass of 10 kilograms. Then it says this has an angle theta, which we know is 20. I'll just put 20 there. I'll put 30, okay, 20 degrees. That equals theta. Theta is just a symbol for angle. All right, now here's the first question. Calculate the weight of the box in newtons. All right, well, letter A, calculate the weight, that's not anything new. We've already done that in the previous chapter. So remember, force weight is mg, if you want to look at it that way. Okay, so it's the mass, 10 kilograms, times gravity, 9.81 meter per second squared. So 98.1 kilogram meter over a second squared. You know, that's not the way I'm going to write the unit. I'm going to write N. Okay, 98.1 newtons. Now, if you wanted to, you could say negative 98.1 newtons. Remember, because technically your weight pulls you down this way. But on this problem, I'm not going to do that we'll just keep that in mind if we ever need to go the other way or whatever, that one will be positive or negative, but we're not going to worry about that. So, all right. First of all, I want to show you, where does the weight, if I said draw an arrow to show me where is the weight force pulling on this mass, you draw it straight down. Okay, so let me go back to my other, oh no. You know what, yellow might look better, I was thinking. Okay, so let's try that. So I'm going to go straight down. There is the weight right there, F. I don't know. I guess I'll write it next to it here. I don't know if I'm going to keep it there long because I know I start drawing things and it runs into stuff. That's the weight, F weight. Weight force pulls always straight down to the earth, always. In your diagrams, you'll let down be towards the center. Okay. Now, what I'm going to do is, as I told you a moment ago, I don't have to worry about if I'm going to push it up or lower it down this ramp. I'm not having to deal with this weight. It's a lot easier. I only have to deal with this component of the weight. So to find the component, let me finish doing the diagram as I showed you. So I'm going to first draw a line. It has to be perpendicular to the slide. That means it has to be 90-degree angle. So I'm going to go like that. All right, I think I did pretty decent. Okay. Now, I'm not going to go all the way to the bottom, okay? Because I have to make a right angle now. I have to come down and make a right angle to connect the arrow to arrow. So right about there. I'll draw it that way. Now, just so things don't get messy looking, let me take away the arrow from one. We know that weight goes down, okay? Force weight goes down. Now, what I showed you a moment ago, since this angle is 20, and we know that this will be 90 degrees. Look at this triangle first. Forget this part. If this is 20 and that's 90, that's got to be 70. If that's 70 and this angle next to it, that must be 20 right there. So you can always just draw your little theta right there. You don't have to write all the numbers around. If I know that's 20 and it says theta is 20, I didn't even have to write 20 there, but in my diagram, that's 20, so that's also 20. If I want to write a little baby 20 below it, I could, just so you know. That's 20 degrees. If that's 20, then that's 20. Okay, now, this is your weight force. Now, this is an interesting thing I'm going to show you. This is going to be F. I'm going to call this Fx. And we'll talk about that in a minute. So, this weight can be an Fx and an Fy. Now, this is also Fy. And I guess, for right now, I'll call that Fy. But there's a better name for that. I'm going to show you in a second. I'm going to put F weight, Fx, Fy. Just so you're good. So you'll be familiar with that already. X and Y component. All right. So letter A, calculate the weight of the block, and we got that. B says calculate the normal force. Now, the normal force. The normal force on the box. I should have put, the normal force on the box. The normal force on the box is the force that is the contact force between the box and the surface. So there's a force between this box and this surface. As they're in contact, there is a force there. Okay? There has to be. The support force. That support force, you think about it, is part of what would have been your weight going down, and it's this component. I don't know if you can tell that or not. So the force between two, when two objects are in contact, the force between those two objects is the normal force. So in other words, when two are in contact, because of gravity or whatever, my hands are in contact, or even if there's this way you're pushing them, when they're in contact, the object A is putting a force on object B, and object B is putting the same but opposite force on A. Remember we talked about that. A puts a force on B, B puts the same but opposite direction force on A. That's the third law. Well, normal force is that way. So what is gravity is pulling the mass in this direction. So you could say that Fy is the only component that's pushing. Gravity is pulling this against the surface in this direction. Now, don't worry about the sliding yet. Let's just talk about the contact only. Fy. Now, this is not breaking through the ramp. If it were, then we got a problem. Okay, but it's not. It's supporting it. So it is being supported by a force in the opposite direction going up. So it's the same as Fy. Fy goes down, but the one going up would be Fn, the normal force. So what I'm trying to tell you is Fy and Fn are both the same. They're the normal force. Fy, and you could say if Fy were negative, the normal force would be positive. So if I know Fy, I will know the normal force. All right? So let's figure out what is Fy. So let me just kind of take off Fn for a minute. Let's just think about Fy. But the normal force is equal to, I'll say the negative of Fy, technically, okay? And we can just let the Fy be negative here. I'm not going to worry about the negative signs here. So it should be technically the negative of Fy, because Fy is gravity pulling you, the weight pulling you down in this direction, perpendicular, and it's a component of weight that goes this way, and the normal force is supporting you going up that way. So normal, okay, by the way, the word normal, you know, in math, it means the perpendicular force. Perpendicular. So perpendicular is normal. So when you say something, oh, Fy is normal to the plane's slide surface, well, that means it's perpendicular to it. Okay, so here we go. All right, so I wrote all this down on the side, but I guess I'll keep it right here. Or, yeah, I'll keep it here. So the normal force, I'll use not sine, will be opposite over hypotenuse. And we know weight. Weight is 98.1. So if you want to write that there, it can help you. Fx over that would be Fx. We don't want Fx, we want to get Fy. So sine is Fx. Cosine of theta will be Fy over 98.1. So cosine theta times 98.1 equals Fy. But I'll write it that way. F normal equals, So cosine of theta equals F normal over F weight. That's the whole thing. Opposite over hypotenuse. Adjacent over hypotenuse, adjacent. So cosine of, what was the angle? 20 degrees equals, we don't know the normal force, over the weight, which is 98.1. If you feel better to put Fy there, that will be okay too. But I'll put Fn, F normal. Okay, now, so 20 cosine is 0.939. No, 940. 0.940 Fn over 98.1. So times 98.1 is 92.2 newtons equals the normal force. And yeah, I've got it on the paper. I put 92.1, but okay, 92.2 newtons is the normal force. All right, so the Fy, and it's Fy for that matter. I mean, technically one is negative. If you want to put Fy there in the beginning, you could, but since it says what's the normal force, I want to show it to be Fn and F normal. All right, and one will be positive, one will be negative. We don't have to worry about the positive and negative in this particular problem, so don't worry about that right now. But anyway, so where was I? So the normal force is 92.2. So 98.1 is this side of the triangle. 92.2 is this side. And then there's one thing left to find is Fx. And there's a couple of ways you can find it. But let me read the question. What in the world is Fx? Okay. Letter C. There's at least two ways you can describe Fx. Look at letter C's question. It says this. Calculate the minimum force required to keep the box from sliding down the incline. Now here's what I mean about making an inclined plane making things easier. Inclined plane classifies as what's called a machine, believe it or not. A simple machine. You don't think about it being a machine, but anything that makes it easier, we'll say on your to get an object up or whatever. It's anything that makes it require less work. So, but anyway, I don't want to say that way. I shouldn't say that. But anyway, I don't want to jump to the next chapter, but it makes it easier. We'll just say it makes it easier. Fx is the force. Okay, Fx is the weight of the object being pulled down Fx, down the inclined plane. So it's the same as this Fx. This is Fx. So here's what it means. You might not be able to lift up this box. It might be way too heavy for you. But if you have the right angle on your inclined plane, and you can make it less and less, make it even easier and easier and easier, but you can actually make that number so small that you can easily hold it up. A little child, like my little girl she's very young, like only in kindergarten, I could get her there and say, okay, look, how about you just do this? Maybe she can be standing near here on the bottom or something, or near the slide. Hold your hand right here against this block. All right, let's see if you can keep it from moving. And she could probably do it. If we have the right angle, it could be a very, very heavy box, like 2 times her weight. And she could be pushing it a little bit and holding it up. But now if she tried to lift that box, she wouldn't be able. When she lifts it, she has to match the weight, 98.12 newtons. But to hold it up here, you only have to match Fx. So Fx is equal to, technically negative Fx, but Fx is equal to the force that you would need to keep that thing, to keep the box from sliding down. Okay, so let's calculate Fx. I guess I'm kind of going sideways here. I'll just do it here. So Fx will be from sine, and we were showing you this when we did acceleration. But sine of theta is Fx over F weight. Am I standing right in front of it? Okay, so sine of 20 degrees equals Fx over 98.1. And then what you're going to do is, we did that a moment ago, didn't we? Sine is what, 0.342 equals Fx over 98.1 times 98.1 is 33.6 newtons equals Fx. 33.6 newtons is equal to Fx. So look at that, just like the acceleration, and in fact it's exactly related to the acceleration of gravity. You know that, because weight is, we use 9.81 there. But if I want to lift the box, I would have to lift up 98 newtons. But to hold it on this particular ramp, a 20-degree ramp, to hold it in place, you would only need to apply 33 newtons, about 1/3. Now that's a big deal. I mean, think about this like, let's just say, let me think about this number for a minute. Let's just say that you weigh about, I don't know, just say that you weigh about 140 pounds. Just say somebody weighs 140. So, could you lift up someone that was 70 pounds? You probably could almost lift your whole weight. You could probably lift up somebody that's half your weight pretty easy, 70 pounds, right? No problem, okay? But what if, could you pick up a person that was like 70 pounds, half your weight? You probably can do that pretty easy. And I just use 140 as an example, okay? I could pick up 70 pounds if you were 140. But if you could not probably pick up someone that was like 200 pounds. No, you couldn't do that. Because 200 pounds, that would be like, no way. If you're 140, that's a lot more. Yeah, gosh, you probably wouldn't be very, very fun. But you could have a 200-pound person, and you could push them up this ramp, because it would only be about, let's see, 200 divided by about 3. You'd only be pushing with a force of about 67 pounds. So less than half of your weight, it'd be a whole lot easier. Oh well, I'm emphasizing that point too much. All right, so on letter C, there's one way to ask the question. It would be, what's the minimum force needed to keep the box from sliding down? Or another way to say this is, what is the force needed to push the box up the incline at a constant speed? Wow. I'm going to have to say a little bit more about that in a future lesson. But I will tell you this for right now. Actually I can tell you I'll give you a quick answer, and then we're going to see it happen later. If I apply a force of 33.6 newtons, and this thing is at rest, what does Newton say? If this is at rest, and I apply a force exactly of 33.6 newtons here, then I am just going to keep it at rest. That's all. Because I'm applying 33.6, and because of gravity down the incline, it's also pushing 33.6, so they're equal. But now, if I can just start the thing in motion, if I can just start that in motion, and I keep applying 33.6, I will continue at a constant speed all the way up. You know what? A better way to tell you this, I'll tell you a better way to say it. A much better way. And you may or may not have ever seen this in your life before, but I'm going to make here a pulley. And let's just say that on the pulley, I put a rope right here. I'm going to come down here. All right. We're going to see some stuff like this later in the chapter. Now, if I put a weight right here that is equal to 33.6, and this thing is not moving at all right now, it's not moving at all, okay, then guess what? It will not move. It will stay in place. This is supporting it and keeping it from going down. Gravity is pulling 33.6. We'll call that Fx, okay? But then your pulley, because of the rug, we're going to say it's pulling 33.6 newtons in that direction for you, okay? So everything is equaled out, no problem. But here's the neat thing. And a lot of times they have this in a window. Like sometimes a window, especially older houses, is heavy. And we have them in chalkboards at school and stuff. And they have a pulley system inside there. And if you lift up the window, there's weights inside the window frame. And so it makes it easier for you to lift it. Have you noticed that? Well, here's the deal. If I went up and I just pushed that real hard, like it's all at rest, and I push it real hard, it will start to move, and it will move at a constant speed all the way to the top. So I could be at the bottom, and I could just go and just give a big push, just get that thing moving, and then it's going to, at a constant speed, it will move all the way up because this 33.6 force is going to be constantly applying to it. Kind of a neat thing. Okay. All right. Last question, D. Calculate the acceleration of the box down the incline if the box is released. This is the last and a very easy question. What will be the acceleration of the box down the incline if it is released? And so, F down the incline equals ma. And so, what is the force down the incline, pulling it down the incline? It would be Fx. It will be right here. So, Fx, I'm going to put in that force, 33.6, equals m. The mass was 10. 10 kilograms times A. So 33.6 divided by 10. I don't need a calculator for that. Do I? No. 3.36. Hey, have you seen that number before? AX. And that's the number we saw at the beginning as well. So that's the way you can get it. You can just divide it out. All right. So I went through a lot and told you a lot of details there. I like this. It's really interesting. But work number 2 and number 3. And that will be all. I'll see you guys.